Hi, this is our second video in Unit 5, the electronic structure of the atom. In this video, we're going to look at Bohr's model of the atom. Well, it turns out that you can excite atoms. What do I mean by that? Well, if you take, say, some gas at low pressure and you apply a current through it, the energy of each atom is going to go up. And that atom, when it's in that lowest state, we're going to call the ground state. But then when we add, say, an electric current or we heat that atom up, that atom is going to go to a higher energy state, leaves the ground state, and it goes into what we call an excited state. Well, these excited states are not stable, and the atoms can't stay in these higher energy states for very long. And so they're going to tumble back down into a lower energy state or back down to ground state. And when these atoms fall down into a lower energy state, they give off energy in the form of electromagnetic radiation. Well, they saw this with hydrogen gas. And what they did is they had a vacuum tube full of hydrogen gas, and they applied an electric current across that tube, and the tube gave off this pink color. And we're going to do this in class tomorrow. Well, when they looked at this pink light through a prism, they didn't see what they expected to see. Now remember, Isaac Newton had looked at white light through a prism, and he saw a continuous spectrum of all the colors of the rainbow. So he saw red, orange, yellow, green, blue, indigo, and violet. But that's not what they saw when they had these excited hydrogen atoms. What they saw when they looked at this pink light through a prism is 4 lines of very specific colors. So here's what we'll actually see tomorrow. You're going to see a red line, and that's about at 650 nanometers, a teal line at 490, and then at even shorter wavelengths, some violet lines. This is what we call the emission line spectrum for hydrogen. And you will see this when you look at that pink light, when we excite the hydrogen gas, when we're looking at that pink light through diffraction gratings, or if we had used a prism. Why did hydrogen give off only specific wavelengths of light? Now let's remember why we're seeing light at all. We're exciting these atoms, and when those atoms fall back down to a lower energy state, it's emitting photons of radiation. And we could actually calculate the energy of those photons of light using this equation that we've used in class already. That the energy is equal to Planck's constant times the frequency. All right, the energy that this photon is emitting is equal to the difference in the energy between those atoms' initial and final states. So each transition from a higher energy level to a lower energy level is releasing a specific amount of energy, has a specific wavelength, and if that wavelength falls in the visible spectrum, we can see the color. We had 4 lines for hydrogen gas, so we were anticipating 4 different transitions. Let's look at what these transitions would look like in this diagram. E0 is that lowest energy state for an atom. It's called the ground state. And then if you go up in energy, you would have to add energy, and so that's called absorption. You're adding energy so the atom can go up to a specific level of energy, or even a higher energy of a higher level of energy. But the atoms can't stay there for long in these excited states, and when they fall back down to a lower energy state, that's where we're getting this emission of a photon of light. Well, at 1885, a mathematician came up with an equation that could explain these different wavelengths of light that were given off for the hydrogen atom, and his name was Balmer. And this formula was relating these various wavelengths of hydrogen's emission line spectrum to his equation. Later on, Rydberg's equation simplified Balmer's equation, and that's the equation you see down here. It's called the Rydberg equation, and if you're in honors chemistry, we're going to be using that a little bit. Well, that was a mathematical model, but we needed a model of the atom to explain what was going on. And so in 1913, Niels Bohr solved the mystery, or the puzzle, what was going on with this hydrogen atom. So he proposed that the electrons were actually the part of the atom that were becoming excited and then falling back down into various energy levels. And it was the electrons in the atom that were causing this light emission. Now, his model of the hydrogen atom looked something like this. So he had Rutherford's nucleus with all the protons and the neutrons hadn't been discovered yet, but he had that positive nucleus in the center of the atom. And then he said that there were orbits where electrons could be. And these orbits were in very specific distances from the nucleus. And that the electrons could be in these orbits. Now, these orbits had different energies. So just to make things simple here on this diagram, this first orbit, the one that's closest to the nucleus, we'll call n is equal to 1. And electrons that are in orbit n is equal to 1 would be electrons with the lowest energy. Then the next higher energy orbit would be called n is equal to 2, and then as you would expect, the next energy orbit would be called n is equal to 3. So electrons are he proposed, resided in these orbits, but electrons could not be found in between those orbits. They had to be at very specific distances from the nucleus. Well, what this diagram is showing here is an electron, that's the green little dot, that is falling from orbit 3 down to orbit 2. And so because it's going down in energy, it is giving off electromagnetic radiation. And we could solve for the energy of that using this equation. Here are the key points to Bohr's model of the hydrogen atom. First of all, electrons travel in fixed orbits, and they are at very specific set distances from the nucleus. The amount of energy an electron has is determined by what orbit it travels in. So the orbits closer to the nucleus have lower energy, and if you're in an orbit farther from the nucleus, the electrons would have greater energy. And there were no electrons that could be found between orbits. Now here's a really big point. The electrons can move from one orbit to another. And if they want to move into a higher energy orbit, you got to add energy. And once they're in that excited state, then they can't stay there very long. And when they fall back down into the ground state or a lower energy orbit, that is the characteristic light that we're seeing for atoms. Now, what about the energy requirements to make these orbit jumpings? Well, for an electron to go from, say, n is equal to 1 to n is equal to 2, it must have exactly the right amount of energy. If you don't have enough energy, nothing's going to happen and the electron's going to stay put. If you add more energy than is needed, well, you'll still go to that next higher energy orbit, but any additional energy, if it isn't enough energy to promote that electron to the next higher orbit, it's just not going to be absorbed by the electron at all. The emission of energy. Now remember, this is when they're falling back to a lower energy. So when an electron goes from the excited state back to a lower state, maybe all the way back down to the ground state, it gives off electromagnetic radiation. And for hydrogen, we saw 4 lines. Now, the fact that hydrogens emit only certain wavelengths of light indicated that the energy differences between these orbits were fixed. It wasn't a continuous spectrum. The electrons can only be here in one energy orbit or another energy orbit, nowhere in between. I kind of think of these energy orbits like rungs on a ladder. You can put your foot on one rung of the ladder or the next rung of the ladder, but you can't put your foot just in mid-air. That's what I think of when I think about these orbital energies for the electrons. And so here's that ladder idea. Here is the n is equal to 1 energy orbit. Big jump in energy to n is equal to 2. Notice that these orbit energies are not equally spaced. N is equal to 3, and then they're starting to get closer and closer together as you go up in energy. So what was happening is this excited electron in the hydrogen atom, if it made it all the way out to the n is equal to 5 orbit, and then when it would fall back down to the n is equal to 2 orbit, it would give off violet light. If we had an electron that was excited and it went to the n is equal to 4 orbit, and then it fell down to the n is equal to 2 orbit, it was giving off that teal color. Wasn't as big of a fall, so the energy given off wasn't as great, and so therefore the energy of the photon, or what we were seeing, wasn't as high of energy as the violet light, so it was the teal color that they saw. And then the red line was from the electron being promoted to the n is equal to 3 line. When it would fall back to the n is equal to 2 orbit, that's when we would see the red line. Again, it's still, from this diagram, looks like a pretty big fall, but it's not as big of a fall as going from the 4 or 5 energy level back down to 2. So it also turns out that there wasn't just electromagnetic radiation in the visible region being given off, but there was some in the ultraviolet region as well. And so a scientist, his last name was Lyman, he saw that some of these electrons in hydrogen, they were in these higher energy orbits, and when they went all the way back down to ground state, they were giving off ultraviolet radiation, and that's called the Lyman series of lines. Now, we can't see in the ultraviolet region. You have to have special instruments to do that. These lines that are seen in the visible region for hydrogen, they're called the Balmer series. And then there are some that only fall back down to the n is equal to 3 region. So that has less energy than the visible spectrum, and that would be in the infrared spectrum. So conclusions. Well, Bohr's model worked great for the hydrogen atom and for other one-electron species, but it didn't work great for atoms that contained multiple electrons because it turns out the electrons influence one another. But this was a great way to start understanding the electronic structure in the atom. And so our next video is going to talk about how the Bohr model was then expanded to how we understand electrons in the atom today. Have a great day.